welcome again to everyone. This is our 13th, I think our 13th seminar for this semester. We have one more to go. One more seminar to go next week, Thursday. And this seminar is different from some of the things that we've seen before. This leans more towards material science. So we will expand our knowledge base from chemistry applied to material science. So I'm looking forward to this. Our presenter today is Julia. So Julia, you take it away. Actually, before Julia does, I need to introduce Julia. Where's my notes for Julia? Oh gosh, I totally forgot I was going to introduce Julia. While I'm looking for it, here we go. Julia introduction. Julia Randall, she majors in chemistry, math, studies, and Spanish. Yeah, wow, triple major. Hometown, Sunnyvale, California. Yeah, that sounds like a really nice place to be from a Caribbean guy. She went to high school at Andrews Academy. Right now, she's undecided about career path, but it does include doing graduate school, working and getting involved in something internationally. Something cool about Julia that I did not know. She started learning Arabic. You want to say a few words in Arabic for us? Hi, hello, whatever, I don't know. Anyway.
I can say I am duo and I'm a queen because that's Duolingo's favorite sentence. That's eine duo wa eine America.
Okay, there you go. Very nice. Very nice. So it's your turn to introduce our speaker for today.
Okay, so our speaker today is Dr. Mkhoyan, who is the Ray D. and Mary T. Johnson Chair Professor in the Department of Chemical Engineering and Material Science at the University of Minnesota, Twin Cities, where he's been a professor since 2008. In 1996, Dr. Mkhoyan graduated Yerevan State University with a bachelor's degree in physics. He then spent 2 years as a researcher at Bell Labs of Lucent Technologies in Murray Hill, New Jersey, before earning a PhD in applied physics in 2004 at Cornell University. Dr. Mkhoyan worked as a postdoc research associate at Cornell and as a visiting scientist at the IBM T.J. Watson Research Center before going to the University of Minnesota. Today, Dr. Mkhoyan will share some discoveries in his work on line defects in perovskite crystals. The study explores a newly found line defect, which is an oxide that is metallic, a finding explainable with DFT-based analysis. This line defect demonstrated characteristics suggesting controllability for engineering, which highlights the importance of such studies to understand ion gel gating and possible conduction and carrier scattering mechanisms in these materials. Let's welcome Dr. Mkhoyan.
So unmute yourself. There you go.
Yes, thank you, Julie, for a very nice and very kind introduction. So, and thank you everybody for attending this lecture. So it's blessed. So we're gonna have fun. I'm gonna take you into the journey of atoms and crystals. So will be fun. So and I'm gonna share my slides and then we'll start to discuss a topic. And I highly encourage you, if something is not clear and you won't like to kind of ask a question in the middle of a talk, feel free to do that. Just unmute yourself and ask a question. That will be more efficient than typing in the chat, because I get excited and then forget to look at the chat, so I might miss it. So just unmute it and ask a question, and I'll try my best to answer everything. So having said that, so I think I can share my slides and then we'll get going. So, and exciting thing, another exciting thing for me, I never talk about this. So this is the first time I'm discussing this topic. So it will be fun. So as Julie indicated, today's discussion, today's lecture, going to be about perovskite crystals and about the defects and about turning an insulating material, basically transparent material, completely looking like a glass, into the metallic conductive one. So let's see if I can, you guys can see my slides, right? Wonderful. So I want to start with something fun and cheerful, sort of. So, and defects in the crystals, they are the outliers. And outliers are everywhere in the world. So, and actually the image here, so with the ship is, that's a type of outlier sometimes I feel during the weeks. So, and well, sometimes you guys might feel like outlier if you feel a little more romantic. So you will feel like a nice different type of flower in the middle of the field. So there are all kinds of outliers. There are all kinds of things that are out of ordinary. But the way I like to think about it, all of these outliers, it will be human way, biological way, and crystals. They are kind of like a spices of the earth. So it's like a spices in our food. You put a little bit of jalapeno pepper in your food, it's a completely different feeling. So, and you put a little bit, I don't know, so anytime you put a little bit of spice into your food, so, and you get a completely different expression of an overall meal you consume. And it's also true for everything in a life. So most of the good things done in this world, so we're done with some unusual fellows around. So it's all good. I would like to say, let's take advantage of it. So now what happens in the crystals? So this is a nice 3D rendering of a crystal. So how these outliers or defects looks like. So let's say I have here nice crystal. So I'll take one atom in it and replace with a different, completely different, that there's no any similarities with the rest of the crystal. Now I get an outlier. Now I get a single defect in it. Sometimes things can be a little more kind of different. So here I have an example when these different atoms are nicely ordered together. So this will be different kind of defects. And they will make like a defect line in this case. Sometimes actually in a crystal, what you will see, that entire crystalline plane is different. So that will be looking something like this. So crystals, like anything else in the world, have outliers, have defects in it. Scientifically, we call it defects, but in a same way, they are outliers. All right, so idea is, can we take advantage, find the good outliers, finding the good defects that can overall change our crystal and the change in a way that the properties will be different. So, and the way we're gonna study these effects and understand how this all works, we need an electron microscope. The reason we need an electron microscope, because with the regular microscope, there's no enough resolution to see this stuff. We need to get into the world of the atoms. So we need the unusual microscopes. So the one that we're going to use, it's an electron microscope. What it allows us to do, several things actually. It will allow us to do some imaging. We can get nice images of the crystal with individual atoms there. We can do also some spectroscopy. Well, now to the main course. So the main thing for our discussion today. What I will do today, I'll walk you through microscopes, transmission electron microscopes, and then guide you through to see how they work, why they are so useful in the science, why we need to worry about them and be really good in that. Once we kind of cover that topic of introduction of the microscopes, I'll also cover basics of this particular crystal we are interested in. Crystal that is completely transparent, completely insulating, but has a lot of fun in it. And then I will go through the actual content of this seminar and this new discovery we made and the new approach we highlight about turning a dull, transparent looking crystal into the spicy, cool, conductive metal. And then I will cover with a summary, and then we'll acknowledge all of the people that were involved in this. And then I can tell you right away, it's all done with the bright students and the postdocs. So I wish I can be back being a student again. So let's kind of think about the microscopes. You would think about the microscope is a relatively new invention. It's like, oh, sounds has a fancy name and all of that. And actually, if you look in the history, they dating back till 424 BC. People are kind of smart even then, so they know how to take advantage of a light and then see in smaller things. But the more real kind of scientifically useful microscopes occur in around the 16th century. And actually, I would like to say one interesting thing here. So very often when we talk about the discoveries that change human progress, very often people think about a light bulb or a wheel. And actually there is one even bigger invention, in my opinion. That's an invention of transparent glass. Transparent glass allowed us to make lenses, allowed all of the people, especially older folks, to be able to get the lenses and then the glasses and be able to read. All of the houses, now they can have a transparent windows and then keep it inside the cool or warm. And actually that light bulb we are all excited about, without transparent glass, is not gonna happen. So, and scientifically, if you have a glass that has a curvature on it, it's gonna look like a lens and gonna act like a lens. And then that allows to you, all of us, to study all of the biology in the level of cells and microbes and all of that. So it helped enormously. So, and that's the story about the regular microscope, optical microscopes. And then comes the 20th century, when we learn about the electrons, and we said, like, electrons are cool too. So we can use electrons. They behave exactly like a light, has an electromagnetic wave moving around. So, and then since the electrons, we can accelerate really, really high. So we can have a wavelength that is very, very short. And that will allow us to see even smaller things. With the regular glass lenses, glass microscope, you will see, you cannot see anything better than a micrometer, maybe just sub-micrometers length scale. But to see the atoms, you need a nanometer and angstrom level things. That's why electron microscopes are useful. Here I have two examples. One on the left, one of the first electron microscope. So looks kind of funny, looks like a pressure cooker, but that's actually microscope. The one on the right is the one that we have in our lab. So that's one of the newest higher end microscope that has so much of a functionality and looks like a more, well, it is a more complicated than Boeing 747. So it's a lot of fun. And even more fun is graduate students go and use it daily basis and having a blast. So now let's kind of talk about a little more about the dimensions. So, well, we'll start with the child. So that's like a good human reference, and especially 5-year-old child, that's the person we like most, and that's the one to create the most of the trouble anyway. So those are on a scale of meters. So now we know what to be careful about. Human eye, as I was telling you about, can detect all things all the way till they're like a human hair. And the smaller than that, it becomes trickier. Then we can use a light microscope, the one I was talking about with invention of glass. So now we can look about smaller things. We can look at the cells and microbes and things like that. And then comes to the electron microscope, which pushes to the resolution on a scale of a 10 minus 10 meter, which is, we are talking about angstrom. So if I'm lucky enough, you guys invite me further, I will also, next time I'll talk to you about imaging electronic orbitals, but that's for another day. So I'm sure you are aware of seeing a picture of this. This is a nice rendering of the coronavirus that make me sitting here instead of being on your campus, and makes all of our life miserable, everybody on the wall.
Yep.
So actually, how this rendering came along, it was originally like a TEM image, electron microscope image, and that's how this coronavirus looked like in real life. It's as ugly as it looks, and it's as much of a pain as it is. So, and atoms, that's where we're gonna be for today. And the level of atoms are on the size of the angstroms. So this is a level of resolution I'm gonna talk about. Electronic orbitals, that goes another order of magnitude low, but as I said, that's a different topic. Seeing atoms is already cool enough. So it's really, really cool. So in a class, in your chemistry class, your professor always talking about oxygen, carbon, hydrogen, they are bonding and all. And then, but if you ask, have you seen it? This is where you're gonna see it. So now about the electron microscopes we're gonna use. There are two types of electron microscopes. So, and the first one, which is original, historically developed, the first one, that's why it's called conventional TEM. What it does, if you have a big beam of electrons, they go through the specimen, they go through the lenses. So the lenses in the electron microscope, it's not like piece of glass. That's for light. For electron microscope, the lenses are magnetic lenses, so they are a little more complicated, but the same idea. You can also use exactly same theory of the microscopes and lenses will be perfectly applicable. But anyway, so electron goes through the specimen, goes through the lenses, and then get projected eventually on a plane. So basically that's your screen, and that's where you take a picture. And then you should get a really nice magnified image of the specimen you have in mind. So if you have a little more money, so I know it's tough, but you can get a little fancier microscope, so which works slightly differently. Instead of having a parallel illumination, you get your microscope focusing the beam into very tiny spot, tiny spot on a size of the smaller than angstrom. And then that electron beam interacts with your sample and scatters off the sample and produce images. Well, turns out it produces not only images, but can produce a lot more fun stuff. But let's do one thing at a time. Let's do first imaging. So let's think about the betta fish. So you can, I'm sure most of you seen in a pet store, and I have one right here on my table. So if you have a fish and you want to image it with parallel illumination, so you put under the beam and your fish gonna look dark. Everything else gonna look bright. So, and that's how it's gonna look like. In a scanning TEM, if you have your same fish and you wanna look it, so you're gonna see a slightly different way. So let's say I have my focus beam. So the focus beam, if it's not hitting the fish, is gonna go straight through the hole of the detector and gonna look like dark spot. However, when I put my beam on an object, in this case on a fish, it's gonna scatter like crazy. And then the scattered beams gonna be collected on this detector, and the detector gonna show stronger side. Okay, so this is all good. So if I take my probe and then raster it like that, I will get a nice image of the fish, which will have a completely reverse contrast than a conventional image. The only, well, what is the fun of this? So what is fun of that is the following. Now I have a very tiny probe. Not only I can do the imaging, but I can put my beam anywhere on a sample and get the local information from that particular point on a sample. And that will be completely different from a different sample. I'm not looking entire object at once. I'm doing one small step at the time, one small point at the time. I'm hoping by now you're getting a little more comfortable how the microscope works. So now let's kind of dig a little bit deeper into it. Let's say I have an electron beam, it goes through the crystal. Unlike a light, electron beam has a charge and electromagnetic wave. When it goes through the sample, it can interact with the atoms of the crystal. When it interacts the atom of the crystal, so it excites the electrons of the atoms of the crystal. So these electrons now going up and down in energy and often emit X-rays with a characteristic energy. So we can take these X-rays that comes out of the atoms and we can identify which atom is which. That's a fun feature to know. We can identify every single atom in a sample. So, but if we collect the electrons that already propagated through the sample, we can, as I was talking earlier, we can get the image of the sample, image of the atoms. And then we can also get this thing called the electron energy loss spectroscopy, or ELS. What it does, I want to kind of get a little bit deeper into that, because I'm going to use the X-rays and then ELS to discuss a topic. Let's kind of look into our world of the atoms. All right, so here I have on the left, simple picture of the atoms, nuclear in the middle. I have a circular picture of the orbitals, so let's say 1s or 2s orbitals. It's the K shell, and then a p orbital, which is an L shell, and so forth. So now let's think about my electron of the microscope goes through the atom and interacts with it. And since the electron is a quantum mechanical object, so it doesn't interact all the time. Sometimes it does, sometimes it does. When it doesn't interact, it's just going through it. So we refer it to elastically scattered electron, and nothing interesting comes out of it. But sometimes this, if I collect this electron in my this ELS spectrometer I was talking about, it will look like exactly original beam. So now if I look at the sum of the other electrons that interact with the sample, they're going to scatter. So they're going to inelastically scatter, exchange the energy and exchange the momentum. And this exchange of the energies and exchange of the momentum going to reflect in their energy loss characteristics. So for example, it could lose the energy of the electron going from one orbital to another, or actually, I think you guys are aware that the electrons sometimes form a sea of the electrons in a crystal. This entire sea of electrons, sometimes that one vibrates too. That's what often referred as a plasmons. So sometimes, remember that X-ray I was telling it? So electron can go from a low energy orbital to the high energy orbital, and that energy exchange on that going to be also reflected in this electron energy loss data. So now let's see if I can go a little bit deeper here. Stay with me. So let's say I got my incident electron, goes and strikes the electron from the atom. This electron jumps into the higher energy. Most likely place it will jump will be the states that are not occupied. If the state is occupied, probably you remember the Fermi golden rule and the Pauli expulsion, that two electrons cannot be on the same state. So basically electrons needs to go to the empty state, and those empty states, it will jump, absorbing energy from the electrons of the microscope. So these available states in the material that it will go, so here I put like a density of those states. And the density of those states, we can directly map by doing this electron energy loss spectroscopy. It will have all of the features of density of states. So basically, we're going to measure all of the available states in atoms and in a crystal. So they have all characteristic energy, so we can know from which atom it happened and what type of specific density of states it has. All right, so that's a cool thing we're going to do using the ELS in our microscope. Now a little bit of summary. So looks like I maybe went a little bit quickly. So let's kind of see what we have. Okay, in our microscope, this is one we're going to use. That's the one a little bit fancy with a focus beam. When the beam goes and interacts with the sample, we're going to collect the X-ray to identify elements, and we're going to use this detector to get a really cool atomic resolution images, and we're going to do electron energy loss spectroscopy to understand electronic properties through the available states in atoms. Well, imaging gonna look really nice. We're gonna look at very nice atomic resolution images, and then a spectroscopy gonna look like this. I think I showed you this slide earlier, so but hopefully now it makes a little more sense, because the spectra, these are basically density of available states. That basically gonna tell us if our material is metallic or insulating and all of that good stuff. So, all right. So now we have this good microscope and we have a basic knowledge how to operate it. We're going to do it. This is a picture of the microscope in a room. So, and why I have this slide in it. So there are a few things I want to highlight. If you want to see the atoms that are like really small on a scale of the angstrom, so you need not only have a good microscope, you need to have microscope located in a space that doesn't have a lot of fluctuations. So basically you need to control the movement of the air in a room. You need to kind of, in this room, temperature doesn't fluctuate more than a degree in weeks. It's like that controlled. So in this room, electromagnetic field of the Earth, even that is canceled. I can probably be safe saying this is the most quietest room in the entire state of Minnesota. If you are in this room and you are not working on a microscope, just sitting there, it takes 5 minutes, you will fall asleep. It's so disturbingly quiet and controlled. So it's fun. So students don't usually these days, they don't let me go into the room because I fall asleep right away. And this is actually microscope portion of it. Microscope is so tall it goes into the ceiling. So okay, so I hope I convinced we have everything in place to look at the cool materials. The material we got really excited about called the perovskite. So there's nothing fancy besides the name. It's just another crystal having a barium in it, tin in it, and oxygen in it. So it has 3 elements. And the unit cell looks like that. If you put periodically all of this, you will get your nice crystal. So only thing a little bit unusual about these crystals, that they have 3 elements. Most often your compounds you have is they have 2 elements, or sometimes it's a single element. This one is a little more exciting in that sense, that has 3 elements, has a little more room to kind of to play with it. This particular perovskite called the barium tin oxide, or actually I might refer to the BSO for a short, but barium tin oxide, it has a really good electronic properties. It's an insulating material. It's dull as it gets, but has a little bit of promise in it, has a little bit of excitement in it. It has a little better carrier conductivity than other perovskites. So, and we're going to kind of use this barium stannite or BSO to understand the defects in it and engineer metallic behavior. So if I put this chart on the left, you will see that BSO in their mobility and the carrier concentrations, it's kind of like a little bit like an outlier among the perovskites. And it's kind of sitting on this corner. Now we thought like, okay, we know these crystals could have line defects in it. We know they're going to have dislocations in it. Dislocations are most common line defects. They occur inside of the crystal on the grain boundaries. But we want to see if there is more to it than dislocations. So the crystals were grown by using a molecular beam epitaxy. It's just a colleague of.
I'm in the middle of something, but I can help quickly. Just like one question.
Yes.
Oh, sorry.
All right, I guess no question. So, and these crystals were grown using a molecular beam epitaxy. So they are relatively thin and well controlled. Here's actually image of that. So in the bottom, I showed you kind of how they're gonna look. It's a thin layer sitting on a substrate. And then if I kind of look at along the plane, so you can see these three images. Every white dot you see, that's a single atom. All right, so now we're talking atomic resolution images. So what you can see, I'm hoping you can see, so sections of the crystal looks like nice and perfect, but there are places with the defects, with these green arrows. You can see it actually, they are there. Sometimes they look like a spot, sometimes they look like planes, so they are there, which is a good news. Good news in a sense that materials has a defects, and we should look carefully what's going on there. So, all right, so we have our microscopes, we have everything in place. Now we're gonna look at the defects, see if we can identify a type of defect that we are after. So I'll give you a few words about the defects. So defects in a crystal can be 4 different types. Can be 0-dimensional or point defects. So they're like vacancies, impurities, dopants. Can be 1-dimensional, like dislocations or disclinations. They can be 2-dimensional, which is like a planar, stacking faults, grain boundaries, or can be 3-dimensionals, and when you have voids or like big interstitials, things like that. So the one that I'm really interested is this 1-dimensional defects. Okay, so those are the ones that takes the minimum amount, but can be more dramatic effect. So that's a topic of our interest. So in a crystals, very often you have these 1-dimensional defects called the dislocations. And then they go from often, if you grow the crystal, it's gonna go from substrate to the surface. That's why often they treat it as a threading dislocations. And you can see plenty of them at the grain boundaries. All right, so dislocations are, here's a kind of what the dislocation is. And then when I have an extra plane here in this crystal, and if I take a loop, you will see that there is an extra plane, the edge of this extra plane that will be dislocation core. Or you can have a screw dislocation. In this case, if I kind of take a crystal and kind of cut it and slice it, so you will get this type of effect. And that called the screw dislocation. It basically, your crystal looks like a screw. And the core of that screw is your dislocations. The funny thing is, entire the history of science, there was only 2 type of line defects was discovered so far. That was this edge dislocation and screw dislocation. And then there is one which is a combination of a couple of edge dislocation called disclination. But this is all we know so far. And actually we were lucky. When we're doing this type of study for a different perovskite, we come across 2 completely new type of defects. This is the other one we discovered a few years back, 2016. It was fun. It was a nice line defect, but it was a metallic. So that ruined all of our hopes and excitation. But we keep working on it. In the case of the barium stannate, actually we stumble on a defect that is indeed metallic. Here's how it looked like. Here's another image from a barium stannate. So you can see a couple of line defects right away. This one actually the dislocation. And this one is in the new one. So how I know it's a new one? So it looks different. And then if I kind of take this one and make a loop around it, so that's a classic dislocation. Loop doesn't close it, as should be the case for every dislocation. In this case, I make a loop, it completely covers. That's odd, unusual, but same time very promising. You can see the structure in the middle is different, so we are on something. we're on something exciting. It is not a dislocation, but it is a full line defect. So we look at this, we saw a lot of this line defect, this particular type of line defect. So sometimes they run all across the film, this BSO material. Sometimes they go only partially, but no worries. They're all there all the time. Here's a few examples of them. Next thing we decide to do, have a really close look at this defect. Here's another very higher resolution. You can see every individual atoms at the core of this defect. We measure the spacing between the central, these two atoms, looks like a pair, and turns out both of them are tin, and they have a particular spacing between them. So I'll get to do that in a moment. So remember the X-ray I was telling you about, that we can get information of every single element in a crystal. Here's on the left is the regular image. In the middle of the image from X-ray, when shows every single atom based on their elements. So from the X-ray, we can get all of the barium atoms here. And then on this image, we can get all of the tin atoms. And we know now what's going on. So this material also has some dopants in it, some point defects in it. So, and they're going to sit in looks like they're sitting in a particular spot. All right, so they're sitting right there next to this line defect we discovered. So this is going to kind of play a little bit the role for our story, but it's cool that we can even see individual point defects around our line defect. So if you look at the tin image, you can see that two pair in the middle, they are indeed the tin atoms. They are not barium, but they are tin. You can see the signal there. So that was kind of exciting. We know what the structure is, and we decide to kind of ask a little bit of advice from a theory people to explain what's going on with our observation. So we took a crystal and removed these two atoms, not supposed to be barium, but we know it's not there. Based on these experimental images, we put the two tin atoms in it. And let's say, let the crystal go wild and relax. So we can do it using a simulation. So we can put it there and let the crystal structure to relax and see what is a low energy configuration. And that's what it is. Looks cool, actually really cool. And actually, when we look at that before and after relaxation, it systematically ends to the exactly same place. And then we can even measure this distance between a tin atom, and it perfectly matched with our experiment. Here it is. Now in this image, when I put all of the atoms together, green is a barium, purple is tin, and then it's basically one by one correlates with this theoretical data. And actually, when we measure the distance, it's almost perfectly matched what we observe in experiment. So here we have a 61 and there is a 75. Well, just a maybe 10–15% difference, but that's not a big deal among the friends. So we did try different things, saying, what about these dopant atoms that's sitting next to it? Is there a reason these guys show up in that location? When we did a little more simulation, try different places, and looks like this dopant atom is like a magnet got attracted to this line defect. So they like to be as close as possible to this line defect. So which means they really like each other. They are like really good friends, which means that they're going to change a little bit the electrons among each other. So, and that's all looks promising. So, and that helps also to see that this tin-tin distance going even closer together. So now we have a structure of a defect. We know exactly what atoms sitting where and how they're bonded to each other. What we can do if we have all of this information, we can put together electronic structure. I'm not sure that all of you are aware about the electronic structure, but I'll try to kind of simplify it so you will be more comfortable with it. So I'm sure you know the atoms bonded together in a crystal. When the atoms bonded together, they share the electrons. If I take all of the shared electrons that happen with through the bonds, they create the bands. So that's where the electron goes from one side of the crystal to another side of the crystal. So if the electron can easily go from one side of a crystal to another side of crystal, like in big one, like a big C, they are metals. So basically there's no any resistance, there's no any barrier for electron to hop from one to another, slightly change the energy. But when your material is insulating, electrons cannot easily hop from one to another because there will be some energies that is not allowed. Those are where the bands are important. So you will learn about that in later years in your chemistry education. So, but simple way to think about it, electrons in crystals, they are moving around, but they have some particular structure. So they cannot take any possible energy. There's some limited limits on that. So this is called the electronic band structure. Looks like this noodle structure, but idea is insulating materials that there are gaps there. Electron cannot have those type of energies. So when we look at this band structure of the defect, what we realize when we have a defect, so these defects make the energy availability completely continuous. Without these defects, so the defects creating these red lines, red bands. If I don't have these red bands, so I will have a gap. If I have a gap, which means that electron cannot conduct easily because there's energies they cannot take it. So that will dramatically reduce their mobility. But these red lines that comes from a defect, comes from the barium and tin and oxygen. So they feel these prohibited energies. Now it's available there, allowing the defect be metallic. So that's all good. So we have a prediction that this defect should be metallic. We all got excited about it because now our defect has all of the hopes and promises and excitement to be metallic. And there is a reason for that. We also have a good sense why is that. So there is a states between tin and oxygen bonds that gonna create the available energy levels in a structure that electron can easily zoom around. So what we did next is saying like, okay, so if these bands are available, what if I add more electrons to the material? If my defect is truly metallic, all of the additional electron needs to get and sucked into this defect. So if that's a metallic, it has to go and sucked into that line defect. So that's what we did. Actually, we in our simulation, we add one electron at the time, see what happens. What we realized, then we add a few more electrons. Actually, now the thinking distance got almost perfect match with the experiment, which means we're on really good path. So experimental data and theoretical now is matching within only a few percent. That's a super promising. And actually, when we looked at the structure where the electrons are going, additional electrons, we see, as you can see in this image, they go and focus into that defect. And actually, if we look at closer look, it goes mostly concentrate to the oxygen. Remember, the oxygen has a 1s orbital, 2s orbital, and a 2p orbital. There's a 2p orbital, which looks like this infinity sign with the two lobes. That 2p orbital is not completely filled. So, but when we added 2 electrons, they went into that orbital and filled it, as was predicted for a metal. That's why you see that these two lobes in all around all oxygens. So this is where the electron goes, fill that lobes of the electronic orbitals of 2p electronic orbitals. Now we got really excited. Now we know our defect is behaving like a metal, acting like a metal. All predictions are there. We need another cool measurement to prove it. That is indeed metal. So, and that's what we did. Actually, this is a kind of, I'm a little bit summarizing where we are till this point. Where we are at this point, we know the structure. We know this defect should create the bands in a previously non-available region of the band structure. So, and that's going to be partially filled because this electron goes and that gets sucked into this defect. So these red bands I plotted here on the side. So that's where it's going to go. So now the question is if we can detect these red bands. And this is now we're going to use electron energy loss spectroscopy. I was talking you earlier. So that's when it's going to be really handy. So what we did, we took our microscope and locate the probe around the individual atoms, one at a time, and collected the yields data. So this yields data locally, very locally, at this atomic level, probing density of states or a band structure, any way you want to think about it. So, and then we're going to see if it's truly the case. So, and then this is the individual atoms, what we are probing. Theory predicts, as I was telling you earlier, especially the atoms like 1 or 2 or 3, they're going to have a strong metallic behavior. That's where the ones that gets this loops filled. So, and then it's going to be less and less metallic as further I go. So these are all these metallic bands that's there. That was a theory predicted. And when we did a measurement, went to the structure and did a measurement, one unit cell at the time, one atom at the time, this is what we got. So we got the reference, we got the for each location, and then going up or down doesn't make a difference. It's all reproducible. We did in many cases, and now we are comparing them. If I compare, like, for example, on a location 3, which is a far away from a core of the defect, and I'm comparing to the further away bulk performance of the material, basically difference is a noise. But if I'm comparing the far away, like bulk material, to the core of a defect, difference is this here. And actually it matches perfectly what you would expect from the theory. And the dashed line in the bottom is what the theory predicts. Now we got our, as my student will tell, that we got the money shot. So basically it's got the perfect match, and then the predictions from the theory that it should be metallic got completely confirmed. And that the shaded region here is that region I was telling you about here that has all of that metallic behavior. And with that, I am on a point that I can wrap it up, and hopefully I convince you that you can take a species of the crystals, line defects, and if you know what's going on, you can have them metallic. And then if you have it metallic, you can artificially grow more of this in a crystal. And then if you grow more of this in a crystal, you will have a metallic lines propagating through your insulating glassy looking crystal. So then you will get the both best of the two worlds. So your crystal, if you look, it's going to look like transparent. But if you connect the electrodes to it through these individual lines of the defect, it's going to behave like a metallic. And that's really cool. So, and that's basically a key message and story about this research, which emphasize again, defects are cool. They are fun. They can change the entire look of your crystal and make it a lot more useful. Again, as like a chili pepper in your food. So with that, I would like to thank other people in my group. So most of the work I presented here was done by Han-Wei. So this is a girl here. She's really, really good. So, and this is a group, all of them doing some crazy fun research, and I cannot be enough thankful for them, and they make my life a lot more enjoyable. And they are, yeah, they are good as I could hope. So, and we also have a lot of good collaborators from theory side, people that are helping to maintain the instruments. And then, of course, we have a government, all kinds of governmental people giving the money and hoping we'll do something useful with it. And I hope we do. So with that, I would like to thank you for coming to the seminar and lecture, and then we'll be happy to answer whatever question comes to your mind.
Very good. Thank you very much for that seminar. I learned a lot. I totally learned a lot. So we want to open up for questions. I have several, and I could begin with questions while others either unmute their mic or put the questions in the chat. So you've basically gotten the science of defects done, which also, I mean, I've read about defects. It's not my, area of expertise or research, but the equating defects and outliers is really a powerful way of thinking about it. And really thank you for that example. But so you've done the science part of it. What is some of the technology applications that you foresee coming out of this research?
Yes. So the way I see where the future takes for this type of stuff, right? So this is a transparent, glassy looking structure. So imagine we can have like a big phone covers or like a regular window. So if you have this material, if you look it looks completely transparent. It looks like a glass. So what it will give you option, you can have it take advantage of all of the transparenting properties and combine with the conduction properties. Let's say you can make some solar cells on your window while it's still transparent. So that will be cool.
That would be very cool.
Yeah, so or make even a different type of touch screens that instead of using a capacitor type of thing, so you can use conduction type of thing. So a lot of cool things can be done. The challenge is at this point we are working on. So if we can find a path, systematically grow these defects in densities and quantities we need.
Right.
So now we're talking about the technology and application, which is a next step from the science to the final product. We do the science, understand the basics, move to the technology development, and move to the product. One step at a time.
Okay. Anybody has a question? You're invited to unmute if you have a question, or you can write it in the chat. Okay, so I don't see anybody, but I have other questions.
Oh, I'll ask one here.
Okay, go ahead.
Yeah, that was a great talk.
Yes.
Nicely well done, and just great information from bottom up. So that was great animations and things. So I really appreciated that. Boy, it's so interesting. I've been, just trying to follow the conductive glass, industry, because that'd be a real big breakthrough, as you said, for touchscreens and all sorts of applications. Yeah, and scaling it up, it's kind of tough, but do you have any kind of sense of what would happen? Because if you get too many defects, that may change the whole structure. Any sense of, what kind of packing do you need for defects before the defects take over and change it into something else?
That's a really good question. So it's an absolutely great question. So there is always a balance. Like I'll bring another example. If we take a piece of crystal and heat it up, so when we heat it up, it gradually creates more vacancies. If we heat it up sufficiently high, vacancies are so much, crystal turn into the liquid. So there is a healthy balance between how much of the defects are good. So same thing, I will go with my original food analogy. If your food mostly jalapeno pepper, you are not eating it. So you will fall on your back. So, and then no friend of you will be dealing with you for a long time. So everything is in the right proportions. So the right proportions, it's that goes back to the technology. It needs to be studied a little more carefully, a little more systematically. So, but the hope is there. That's my message. Hope is there. Just let's people do a little more systematic work.
That's just such a great breakthrough to realize you can get to that metallic state, you know, from prediction and then from experiment. So this is just in one type of material. Does this kind of give us the idea that other materials, we can create defects in other materials to do it?
Yes. Inside of this, I have a good sense what is really key to it. So I asked my colleague who is growing the crystals to kind of grow the type of crystals I believe it's going to have even more, or maybe instead of a line defect, we'll have a planar defect. So we're working on it. So I think we have a key understanding what drives it. So
that's great. Yeah, fantastic.
Does that also imply that beyond the barium tin oxide, you're looking at other combinations of mixed oxides?
That's right.
Okay.
So, so that if the key part I'm finding here exciting. So in this defect, the bonding between a tin and oxide that creates that filling that space. If we take advantage this tin oxide bonding, so we can take many other perovskites into the metallic because it has about the right type of bonding between them with the right amount of energy.
Okay, so the tin oxide is critical, at least at this point, is what you're observing.
Yes, so which means that in every perovskite, if we look carefully, all of the individual bonds and see where they're located in their band structure, we know which one to tailor, which elements are more sensitive about it.
So I'm assuming too that the defects are random. Does that mean, or it may not be, I don't know. Will they be found, if you get multiple samples of barium tin oxide, will they all show defects that are metallic?
Yes. Every time you see this defect in it, it's going to be metallic. What we have so far, the way we grow, so our defects, we can have a priority in which direction to grow. So the way we have it, since we are doing a nice MBE grown, by controlling a substrate, we can have enough stresses. We need a little bit of stress to get these defects going. So, and then we're controlling by substrate, we have a directional growth of this line defect. So which already big plus, we already have a directionality of it. So we already have some level of control of the defects growth, which will be important for the technology.
Okay. So yeah, I think, so basically what I'm learning is that crystals generally are not perfect.
Yes.
The defects in the crystals could increase electron mobility, which could then make them conductive and metallic. Is that a summary for the general public, if you will?
Yes. So,
okay.
Yeah, I like it. So.
Okay. All right. Anybody else has questions? So Ryan, actually, I have a question. Do we teach to what degree do we teach stuff about crystal structure and defects and stuff like that in GChem?
Very, very little. And I feel like it's getting cut out even more, which is sad. It's one of the areas that I actually enjoy teaching in general chemistry because there's some nice patterns there. And we never got into defects though. Just learning, simple crystal structures and making some simple calculations. Such a great way to, take your three-dimensional knowledge and try to build. And, but just the school year seems to be, we're changing so much. We've had to got to cut a little bit out here, a little bit there.
I know.
And I feel like our crystal structure stuff has suffered a little bit.
Right, right. Yeah.
And it's such an exciting area. It's like which kid do you kick out of your family? And it's been it's been rough.
It's been, yeah, because I mean, for example, I think this is maybe getting away from the topic, but to what extent do you do nuclear chemistry? Well, I don't like nuclear chemistry as a word, as a phrase, nuclear science.
Mhm.
It's in the back of the book chapter.
Well, we get to it. We get to it and we're doing it. So yeah, we could get into those topics, but yeah, I mean, general chemistry is such a glancing blow on so many of these topics, and so we just give them a little taste of it, and hopefully they'll find some interest in it.
But we do cover even in high school, we do cover the idea of a sea of electrons in metal.
Mhm.
But I don't think, at least in high school chemistry, I've never really talked to them about the bands. They know about
Yeah, we don't get into it too much. It's in the textbook. We just kind of flying through it to get some information about the solid phase and a little bit of crystal structure. So, yeah.
If you guys have a room for one more course, there is a absolutely fantastic book by Callister called The Introduction to Material Science.
Hmm.
And that book, absolutely great textbook. If you cover it one semester, you will go about all of it. And the only thing you need is a basic chemistry.
Okay.
I wonder if that's what our engineering guys, they take one semester from us, and then
Okay, there it is.
they might be using something like that.
Yeah.
That's the book. I used to teach that a lot, so
Okay.
I'm having way too much fun. They took it away from me.
That's the way it goes.
Okay.
Everybody want to teach this course. It's a lot of fun.
Yes, it does sound like it.
Yeah, make it fun, or it's not worth it. Yeah.
Anybody else has questions? Okay, well, we will be checking back with you in a couple of years or so. See
That was
if
great.
we make any technological breakthroughs that we all need to be buying Windows from you or something. I don't know. But
Sure.
thank you so much.
It was a blast. Thank you
Yeah,
very
that
much.
was
for inviting me.
great talk. That was fantastic. Thank you for
The
sharing your
analogies
time with us.
were, the analogies alone, man, was spot on.
Yeah.
You guys gonna remember about the chili peppers, right?
Exactly.
So the spices, that's what makes everything
Yes,
fun.
yes.
Yes.
Totally agree. Totally agree.
Yep. All right. Thank you again. Take care. Bye-bye.
Bye-bye.
All right. Take care. Thanks.